Hello, welcome to my talk on wave energy conversion. In this talk, a short introduction to the mainstream of the wave energy technologies will be given, including the technology classifications and the corresponding wave energy conversion principles. In this talk, I will discuss why we have not seen and will not see in near future the technology convergence as we have seen in wind energy. In this talk, I will also introduce the successful technologies, the technologies in high-level development, and the failed technologies, together with the discussion on the challenges for wave energy technology and the possible solution to the difficulties in wave energy development. As we all know, currently we have many different types of wave energy conversion technologies. All have their own advantages and disadvantages in different aspects. And there is no consensus at all on technology convergence, and there will not be in the near future. This is very different from the wind and the ocean current power generation, where the technologies are converged to the three-bladed horizontal axis turbines. Following Falco, the mainstream of wave energy technologies can be classified to three different types: oscillating water column, including fixed or bottom standing and floating devices, which convert the wave energy into the pneumatic energy in the primary energy conversion, the first stage of energy conversion. Oscillating bodies. This category covers the largest portion of the wave energy technologies, including all the devices converting the wave energy into the mechanical energy in the primary energy conversion. The overtopping devices, which convert the wave energy into the potential energy in the first stage of energy conversion, when the wave energy is concentrated together with the wave shielding effect. We will see more details on these wave energy conversion technologies later in this talk. This simple but rather clear classification is mainly based on the types of power takeoff systems. Principally, the main types of the power takeoff system in wave energy technologies: air turbines, hydraulic or linear electric generators, and low-head water turbines, respectively. A different technology classification can be found in the website of European Marine Energy Center, mainly based on the device deployment and the energy conversion principles, including attenuator, point absorb, oscillating wave surge converter, oscillating water column, overtopping devices, and many other different types of wave energy converters, including the submerged pressure differential devices, barge wave energy converter, rotating mass, etc. If we compare these two classifications, we can see here number 6, 7, and 9 are not included in the Falco's classification. In details, an oscillating water column wave energy converter is basically a hollow structure which is open at both ends to the water and to the air. Under the wave action, the water surface inside the hollow structure can move up and down, which could drive or suck a high-speed airflow through the constructed air passage and the air turbines. OWC can be either a fixed structure, such as limpet. It is an onshore OWC standing on the cliff and facing the incoming wave in the sea. Under the wave action, the water surface in the water column would move up and down and thus drive the air flow through the air turbine to convert the wave energy into the electricity. OWC can be also a floating structure, such as the famous BBDB, the backward bend duct buoy, which could use the structure pitch, heave, and surge motions, or their combinations, to convert wave energy into the pneumatic energy and then to electricity. Oscillating bodies are the largest category in the wave energy technologies. All wave energy converter convert the wave energy into the mechanical energy in the primary stage of energy conversion, the first stage of energy conversion, and then to electricity use the hydraulic or linear electrical generator power takeoffs, or to other types of energy, for instance, for desalination. The examples include the bottom standing point absorbs, such as the core power wave energy converter, or the floating point absorbs, such as the wave bob wave energy converter, or ocean power technology OPT. This category also includes the oscillating wave surge converters, the hinged flaps, which fixed either on the fixed foundations or on the floating structures, would move oscillatingly under the wave action. So for converting wave energy into mechanical energy and then to electricity, the developed oscillating wave surge converter include oyster and wave roller. The attenuator wave energy converter, which are basically floating multibody devices, and the relative motions between the bodies can be used to convert wave energy into mechanical energy in the primary energy conversion. The famous example is the Paramus wave energy converter, which would have 4 or 5 hinged segments for converting wave energy. See the picture here. Overtopping device uses their wave energy concentration and wave shielding when the wave reaches the shallow water before the storage tank, and the wave lumps over the height into the reservoir. See in this plot the fixed overtopping device, and the wave lump over height into the reservoir. The wave energy is converted into the potential energy in the first energy conversion stage, and the stored potential energy can be then converted into electricity using the low-head water turbines when the stored water returns back to the sea. The overtopping device can be floating as well, with the famous overtopping device called the wave dragon, which is a huge floating overtopping device. For converting wave energy into the useful energy, generally we have 3 different energy conversion stages, from waves to electricity. The first conversion stage is via the wave structure interaction. The wave energy is converted into different types of energy depending on the wave energy conversion principle to pneumatic energy in OWCs, to potential energy in the overtopping devices, and to the mechanical energy for the oscillating bodies. To further convert the converted energy into the more useful mechanical energy for electricity generation, power takeoff PTO system would be used. The air turbines for pneumatic energy, the low-head water turbine for potential energy, and the hydraulic or linear electric generator for the mechanical energy. And the third stage of the energy generation is the electricity generation by connecting the PTO to the electric generator. After that, the generated electricity can be connected to the grid through the relevant substations. Currently, there are 4 different types of power takeoffs, and these are most popular power takeoff systems. However, they should not exclude the other power takeoff system, such as the specialized mechanical power takeoff system, the piezoelectric energy converters, etc. Based on the types of the converted energy in the primary energy conversion, different types of power takeoff system must be used. For pneumatic energy, air turbines are used, including the impulse turbines, as seen in this plot, or the Wells turbine seen in this picture. For the mechanical energy, hydraulic system can be used. See this drawing and the picture for a real hydraulic cylinder. Or use the direct linear electric generator to convert the mechanical energy direct into electricity. See here. And for the potential energy, low-head water turbine is employed. See the drawing, which is what I can find from the website for free use. Here it is only used for illustration. It might be different from the real low-head water turbine. Why there are so many different types of wave energy converters? The reason for this might be the different environments in the sea, different water depths, such as the deep water or shallow waters, different wave conditions and resources, the open seas, or the sheltered area, or the coast areas, etc. In fact, we may find some similarities from the ocean platforms. See this picture. From the picture, we can see we have the bottom fixed structure in the relatively shallow water, generally up to about 500 meters water depth. Then we have tension-necked platform in deeper waters. If we go for deeper water, we can have the spar or semi-submersible platforms. And we can also have the floating production, storage, and offloading systems. All these platforms serve for different purposes For instance, TRP, the tension leg platform, which is specially used for reducing or removing the heave motion of the floating structure, because this is the most difficult motion mode for the drilling facilities in operation. Relatively, other motion modes, the pitch, surge, or sway, can be rather easily handled by the drilling facility. It should be noted the tension leg platform is very expensive for the mooring system, the expensive tendons, and the expensive installations. However, for crude oil production, the return can be huge when the oil price is high, as we have seen a few years earlier. Therefore, we can understand that due to the complexities of the ocean environment, different wave energy conversion technologies have been proposed, and very likely we will not see the technology convergence in the near future as we have seen for wind energy. In the development of wave energy technology, we have seen some successes as well as failures, and the dominant issue would be the failures of wave energy technologies in the recent years. In fact, there are some successful stories in the past, and more important, researchers around the world are making their efforts to advance the technologies and bring the green energy from the sea. Many developments are happening around the world, and I will make some introductions on this topic. In the next two slides, I would like to introduce the most successful stories in wave energy utilization and production. The first example is the most successful wave energy utilization, the wave energy powered navigation buoys, which was invented by the Japanese inventor and pioneer Yoshio Masuda in 1940s. The idea for the invent is to provide the power for the navigation buoys in the remote areas, so for removing the requirement for replacing the batteries for the navigation buoys. The development was in fact very successful, with 700 navigation buoys made in Japan and the other 500 sold to other countries, including 20 in the US. Currently in China, the similar development is still ongoing. Another successful story, I would say, is the Limpid in Scotland. The land installed marine power energy transmitter, a shoreline OWC wave energy converter. See the front view of the Limpid plant and the drawing for illustration of the wave energy conversion principle. The wave energy plant had been in operation from 2001 until 2013, making it the first wave energy plant to generate power to the grid from waves for more than 10 years. Following are some facts from the reference. By 2011, the plant has been run for more than 75,000 operating hours, and the plant has achieved over 98% system availability during its last 4 years of operation. The plant was shut down in 2013, unfortunately, and then a decommissioning was made. This is the picture for the limpid plant after the turbines have been removed. The main reason for shutting down the wave plant is the economic consideration. The power generation from the wave is too expensive to make it economically viable. It should be noted this is the reality for all wave energy technologies, even if all other technology issues are solved. For instance, the reliability and the availability of the wave energy production. Hence, we can see there is a catch here. How can we prove our technology and then make the reduction of the energy cost in a lengthy and costly process, while the financial support asks for the return in a short period? In the next 3 slides, I will introduce some promising technologies for wave energy conversion and production. All these technologies are in high technology readiness levels or in real sea trials. The first example is the OE-Buoy, the floating oscillating water column wave energy converter, which is a backward bend duct buoy, uses the structure motion, pitch, heave, and surge for wave energy extraction. The development of the OE-Buoy technology has gone through the real sea trial for the quad-scale model, and both wheels and impulse turbines were tested during the test period for over 3.5 years. Currently, a 4-scale OE-35 with a capacity 500 kW was built and towed to the wave energy test site in Hawaii, US, and the planned sea trial would last a year. You can find more details in the website, the link here. Machiko Wave Energy Plant is a fixed OWC wave energy converters, which were built in the breakwater. See the breakwater, the red arrow points to here. There are 16 OWCs, each equipped a power generation of 18.5 kW. Hence the plant totals 296 kW. This plant is currently generating power to the grid, and it has been used for a test plant for the control technologies in the OPRA project and EU Horizon 2020 project. Another wave energy generating OWC is the Yongsu Wave Energy Plant in South Korea, which is an isolated bottom standing OWC with an installed power capacity of 500 kW. The author understands that this wave energy device is generating power to the grid, but not much information can be found for this wave energy converter from the website, and some details can be only found in the reference here. In this slide, 2 different point observes would be introduced. The first one is the OPT, the Ocean Power Technologies, US, which has been in the technology development for many years, and from their website, it can be seen that the PB3 buoys have been generating power, but with only a capacity of 3 kW. Currently, Not much information reported or available from their website. The second point of observe is the core power buoy, which is a bottom referenced point of observe. Core power is a relatively new technology, but the advancements of the technology have been great. And recently, the half-scale model has been tested in the European Marine Energy Centre in Scotland. The author has been hoping more information can be available for this wave energy converter. In addition, there are many other developments in the wave energy technologies, including the Eagle device in China, C-Lab in France, and etc. In the next 2 slides, I will introduce the failures of the technology, especially the failures since 2013. Most of the failures are technological failures, but also some operational failures. The author hopes we can learn something from all these failures, although it would be difficult, since no report on the root cause of the failures has been made. The first failure introduced here is the wave-bob device in Ireland. Wave-bob is a floating point of observe. See the drawing. The original power takeoff is the hydraulic system, and the reason of failure is not published, but the author reckons it is the PTO system. This might be understood from the fact Wave-bob had a plan to change the PTO from hydraulic system to direct linear electrical generator shortly before the company went into administration. The second example is the Paramus, an attenuator wave energy converter, which has been once the most advanced wave energy technology. In the development, 3 original Paramus devices have been constructed, but never actually generated power. And then 2 newer version P2 devices have been constructed and bought by E.ON and Scottish Renewables, respectively, for extensive sea trial in EMAC from 2010 to 2014. The reason of the failure was not published, but again, the author reckons it is with PTO system. Here, I would like to show some facts about the P2 sea trial. The sea trial covers a period from 2010 to 2014 for 2 machines. They generate power about 12,000 hours, and the generated power is about 250 megawatt hour to the grid. Based on these figures, we can calculate the average power generation about 20.8 kilowatt. If we compare this to the capacity of the machine, 750 kilowatts, so the power generation is actually less than 3% of the capacity. The third example is the aquamarine oyster, the oscillating wave surge converter. The device uses the oscillating flap for extracting wave energy. The power takeoff is hydraulic system, and the reason for the failure was not published, but It is reported the failure was triggered by a mistaken operation on a valve, but the root cause might be the hydraulic PTO system. Since the author understood Aquamarine had a plan to change the power generation from onshore with the pumping system to the device, the PTO would be within the device shortly before the company went into administration. The fourth example is Oscillating, the oscillating water column wave energy converter. In fact, there were two failures in the development. The first failure was due to the mooring failure for a floating OWC, and the device broke away and sank onto the seabed. The second failure was the accident of the seabed standing OWC during its towage from the building site to the deployment site, and the airbag for floating the OWC broke, and the device sank onto the seabed. You can find the photos if you search Ocean Links. Now the technology, the IP, brand, and the trademark were all sold to Wave Power Renewables Limited in Hong Kong for further development of the technology. In this slide, the challenges for wave energy technologies are given. All wave energy converters must experience the severe irregularities in wave amplitude, frequencies, and directions. Thus, design a device which can extract wave energy efficiently in a wide wave condition would be very difficult. All wave energy converters would have survival problem in the extreme weather condition, which might mean a possible 100 times larger loading than that of the operational loading. A common difficulty for wave energy converters is their large force and low speed due to the wave. Thus, how to improve the device reliability and the energy conversion efficiency would be the key factors. Most wave energy converters need to convert the slow motion of the wave of about 0.1 Hz to the regular energy supply of 50 or 60 Hz, a frequency of 500 times larger. And stop is a common problem for most WECs due to the inherent limit stroke of the PTO. But it might cause significant loading on PTO, thus make the PTO less reliable. And we have also many difficulties in engineering implementations. Here, I would like to talk about my personal opinions on the wave energy technologies, which are purely based on my personal understandings and experience. The author believes that the difficulties number 3 to number 5 in the previous slide could be principally conquered by using oscillating water columns. The advantage of the oscillating water columns, including the wave power, can be converted into the high-speed airflow directly. Thus, a much smaller force would act on the OWC PTO, which are very beneficial for PTO, reliability and survivability. No joints or articulations on the OWC wave energy converters. The disadvantage of the oscillating water column wave energy converter is the efficiency of the air turbine, since the self-ratifying air turbines are generally very inefficient. But great advances have been and are being made in IST in Portugal and Switzerland in US to improve the energy conversion efficiency for air turbines.